Thomas Koberda from Virginia, and he's going to tell us about regularity and group actions on one-manifolds.
Thank you all for coming. It's a pleasure to be here in Oberwolfach. Thank you to the organizers for inviting me to speak. So yes, I'd like to talk about groups acting on compact one-manifolds and the effect that regularity has on the algebra. So various of these results will be joint with Beck and with Sangman Kim, and others will be joint with Yash Loda and also with Kim. So the main motivating thing that I like to do is I'd like to present sort of an organic development of ideas, which unfortunately doesn't actually represent how these developed in real life, but I hope will motivate them, what I'm going to say, fairly well. So I'd like to consider mod S, the mapping class group, of a surface, and S has some genus, some possibly number of punctures or mark points, and some number of boundary components. When it's not important, I'll just suppress that from the notation, and I'll be interested in mod S and its various subgroups acting on M, which is secretly S1, or the closed interval. So in any case, M can always just be taken to be a compact one-manifold, so a finite disjoint union of circles and intervals. And these actions are always assumed to be faithful, and at least by homeomorphisms. And the thing I'd most like to discuss are restrictions imposed by assuming that they are diffeomorphisms of which are ck, or some k which is equal to 1 or 2 most of the time. So the classical story that we have is the work of Nielsen. And what Nielsen said is you take mod of S, where here S is going to be a closed surface of genus G with one marked point, which one can also think of as a puncture. And this group injects into the group of orientation-preserving homeomorphisms of the circle. This is a classical result, nearly 100 years old. And so the way that this is viewed is one takes a mapping class and lifts it to a homeomorphism of the surface, and then you can lift that to the universal cover, and the hyperbolicity of hyperbolic space gets you an action by a homeomorphism on the circle at infinity. And there's a pi 1 of S's worth of ambiguity for choosing the lift, which is why you needed the mark. Okay. So the homeomorphisms by which this mapping class group acts on the circle are quasi-symmetric, and they have a lot of sort of inherent irregularity to them. They're not differentiable anywhere, really. Most of them are not differentiable. So there's a question that I think was, from what I understand, was raised originally by Labourie around 1998, which was, can Nielsen's action, or in fact any action at all, be smoothed?
You mean like, is it topologically conjugate to a smooth action? Or?
So that's, right, so but not necessarily just Nielsen's action, just any action at all. So, in other words...
Can you move out of the shade?
Oh, yeah, yeah. Is that better?
Yes.
So, in particular, questions like, so you look at the mapping class group of a surface, does it embed in, say, diff k of S1, the k times differentiable diffeomorphisms of the circle. So, for the entire mapping class group, this was shown to be false by the results are due to Farb and Franks. There was some independent work on this by Etienne Gis, and they say that that the entire mapping class group mod S does not embed into diff2 of M, where here M was the interval, or S1, and S has genus at least 3 and 0 or 1 marked ones. Okay, so maybe this was sort of the end of the story for diff2. There was also an improvement in terms of regularity by one of Frank's students, Kamlesh Parwani, proved that you couldn't get a C1 action. For genus at least 6. Okay, so in this result of Farb and Franks, and of Gis as well, the important feature here was the existence of lots of braiding relations. And for Parwani's theorem, one uses the braid relations, and then to get the C, so the C2 methods used here are this sort of classical Denjoy-Coppel sort of lemmas arguments. And in C1 actions, for C1 actions, it doesn't have those anymore. And so Thurston stability was the important method here. But it relies on the ideas in here in an essential way.
What is Thurston stability?
Thurston stability says that if you have so one way you can think of it is you have a group acting on a one manifold and has a fixed point. And you look at the germ at that fixed point, and it has a surjection onto the real line. Non-trivial homomorphism to the real line, as viewed as an additive group. So in particular, its first Betty number is non-zero. So it's a theorem about foliations as it was originally stated, but that's sort of the dynamical consequence. Okay. So maybe this was the end of the story for mapping class groups, but there's this sort of analogy one thinks about in the theory of mapping class groups between mapping class groups and lattices in higher rank semi-simple Lie groups. I guess if one's careful, we can put semi here. So the idea is that the mapping class group shares some properties with lattices in higher rank Lie groups and others with ones in rank 1 It's really neither of them in any precise sense. But as far as actions on one manifolds go, the theory of higher rank lattices informs us a little bit. So there's this result of Berger-Monod, which was in the real rank case built on work of Whitty-Morris, in the case of Q rank at least two. It says, so if gamma instead of G is a lattice in a higher rank simple Lie group, then the following holds. So any C0 action on the circle has a finite orbit, and any C1 action factors through a finite group. So there are very few non-trivial actions.
So they prove that even for uniform lattices?
I believe so, yeah. So now for mapping class groups, well, what can one say? So we have these results here for the whole mapping class group, but a lattice is only defined up to commensurability. So the corresponding theorem should hold for all finite index subgroups. And unfortunately, finite index subgroups are very complicated for finite index subgroups of mapping class groups can be very complicated and they're difficult to understand. And what's more is that the methods that were used here don't apply to finite index subgroups because braid relations, they disappear after you pass to a finite index. So, however, one still has the following. So if you, so I'll write C of S to be 3G minus 3 plus n. So this is the size of the largest multi-curve on S. So we're here n includes both the punctures and the boundary components. And so the theorem is that so there exists a finite index subgroup gamma of mod S such that gamma embeds inside of diff 2 of M, where M is here again any compact one manifold.
So anyone, not just this.
Yeah, any compact one manifold, if and only if C of S is less than 2. So,
C.
yeah. So this is saying that there exists such a finite index subgroup if and only if the mapping class group is virtually a free group across a cyclic group, in which case such actions obviously exist. So that's that. So let me say a few words about why, how this works, and sort of, if you were hoping that I wouldn't talk about right-angled argument groups, I tricked you. So, in order to understand mapping class groups, we used right-angled argument groups because they persist in every finite index subgroup of the mapping class group. So this is a completely general phenomenon. So let me just give a definition here. So if gamma, I should use gamma. If X is a finite simplicial graph, and V of x are its vertices, and E of x are its edges, then the right-angled arc group A of x is just generated by V of x and two vertices commute if and only if they span an edge. Okay, so right-angled arc groups have this very simple property which is extremely useful for studying finite index subgroups of mapping class groups. Namely, they have these injective endomorphisms that when you take any vertex that generates the right-angled arc group and you replace it by any non-zero power, you get the same group back up to isomorphism. So it's an injective endomorphism from the right-angled arc group to itself. So in particular, what is true then? So if G is any group and H a finite index subgroup, and if A of x is a right-angled arctan subgroup of G, then this implies that A of x is also a right-angled arctan subgroup of H, not necessarily the same copy of A of x, but some other. Okay. So then, there should be some sort of bridge now between right-angled arc groups and mapping class groups, and so that comes through the curve graph. So the curve graph, just to remind you, so C of S is the curve graph of S. So the vertices here are isotopic classes of non-peripheral simple closed curves that are essential. And edges are given by disjoint realization. So there's a theorem which is actually true in somewhat greater generality, but it's good enough for what I'm going to say, is that if x sits inside of C of S is a finite full subgraph. So you just take some finite collection of vertices here and you look at the graph that they span. Then this right-angled arc group A of x sits inside of the mapping class group mod of S. And there's you can be actually very specific about what this homomorphism is. Namely, if you name this map here I, then there are many maps here, call them I star n, where here I star n, it sends a vertex of x to the Dane twist about the curve I of v, given by the image of that vertex over here, and then takes it to the nth power, and this is injective. For n sufficiently large. Okay. So then the real theorem that implies this one is you consider the following graph, call it P4. P4 is the graph that has 4 vertices and is a path. So the real theorem that that A of P4 does not sit inside of diff2 of M for any compact 1 manifold.
Is that does Z to the 4?
No. No, this is,
No, that's supposed to be full.
So this is the real theorem, and then this now follows once one observes that this complexity exactly tells you when P4 sits inside of the curve graph of the corresponding circle. It's exactly when the curve graph is connected and has infinite diameter. So just some remarks about this theorem. So there are two things that are essential here. One is the twice differentiability, and one is the compactness of the manifold. So first for twice differentiability, so there's this other theorem of Farb and Franks. It says that if G is finitely generated and residually torsion-free, nilpotent, so this is a very large class of groups which encompasses all right-angled arc groups, then G sits inside of diff1 of M. So here M is in fact any one manifold, but in particular compact ones. So 2 here is the best that you can do. There's actually, you can prove this slightly, but I don't really want to get into the details too much. So you can replace 2 plus once differentiable with first derivatives of bounded variation, but that's absolutely the best that one can do. And then for compactness, there's a separate result of the 3 of us, which says that any right-angled arc group embeds in diff infinity of the real line. So if you drop compactness of M, then any right-angled arc group acts by C infinity diffeomorphisms. So
I assume that, is it known whether the mapping class group acts by C infinity diffeomorphisms are?
so it's not even known if in general it acts by, even vert after passing to a finite index subgroup, it acts by homeomorphisms, except in the case where you have a boundary component. But in that case, I'm not sure.
Okay.
Yeah, there's this whole thing about whether the mapping class group is virtually left orderable, which is open. Okay. So before I go on, I'd also like to note some other corollaries of this, which don't follow from this result formally. Namely, so no finite index subgroup of the following groups embed in diff2 of M for any compact 1 manifold again. So the braid group on n strands. There's also the Torelli group, I sub G for G I sub G, and for any G and G greater than or equal to 3. And then you can also consider the Johnson filtration, J sub K. For anything, so this actually also works for the Johnson kernel, g greater than or equal to 3 is good enough because you can realize P4, A of P4 by separating Dane-twists on a surface. And then for general terms of the Johnson filtration, you need G at least 5 as far as I can tell.
Do you know, does it follow from any of this, whether F2 cross F2 embeds or doesn't?
It does.
It does?
Yeah.
Is it clear?
Well, you can, just a product of two free groups.
Yes.
Well, on the interval, you can just cut it into two pieces. You take any two generic things over here, any two generic things over here, they give you F2 cross F2. But there's a related question. If you take F2 cross F2 and then you want to throw in a fourth diffeomorphism and hopefully generate F2 cross Z, then that's unknown. So that's about all I'll say about that. So now I'd like to change gears a little bit and talk about some other groups acting on one manifolds and how regularity influences them. But it's related to how right-angled Artin groups act on or don't act on one manifold. So the original sort of naive approach that we had to prove theorems or disprove theorems like this would be, well, you take a chain of intervals. So this is what I mean by this here is I have these intervals that are sort of interlocking like this. This is all sitting inside of a larger interval, if you please. And you have F1, F2, all the way to Fk. Homeomorphisms possibly with some higher degree of regularity. And then one can consider what's this group generated by F1 to Fk. And I mean, one of our original thoughts was, well, F1 commutes with F3 here, but it doesn't commute with F2, which commutes with neither F1 nor F3, and maybe you get sort of the right-angled Artin group on the anti-path. So you would have X be the anti-path of length K. So meaning that you just take the path on K vertices like I have there, and then you complete it to be a complete graph, and you delete the edges that were in the original one. And then maybe this would be the corresponding right-angled Artin group. And so I was playing around with this one day, and I realized that this is obviously false, because if you consider the following setup, so just take A, B, and C, and 3 homeomorphisms like this, whose supports are exactly these 3 intervals, and they interlock exactly the way that they're drawn. So suppose just, after replacing B by its inverse if necessary, I can just assume that B moves all points to the right in its support. So then, if this naive conjecture were true, then A, B, and C should generate, well, A and C commute with each other, so that should be a Z2, and this one commutes with neither of them. So this should be Z2 direct sum, free product Z. But if one considers the following, well, if you apply B and then A and then B inverse, you get a homeomorphism whose support is properly contained inside of the support of A. And that commutes with C, so and that's bad news for this being true. So this is obviously not the right thing to look at. But then, maybe one can salvage even a simpler case. But if you just take two homeomorphisms, so say F and G, and I just say, okay, what do F and G generate? I mean, who knows? I mean, this could be an extremely complicated group, and it's sort of absurd to even hope that one could pin this thing down. But if I impose sort of a very innocent-looking dynamical assumption, which can be guaranteed by replacing either one of F or G or both of them by some non-zero power, namely, so let's call this point here X, and I'll call this point here Y. So if I assume that if G composed with F applied to X is at least Y, then it turns out that this group is isomorphic to Thompson's group F. And I think this was sort of folklore for a long time. I learned this from Yash Loda, and it was sort of mind-blowing. I became a converted skeptic about Thompson's group, to be totally honest. So let's use F here. I mean, so these assumptions on F and G were just that they're homeomorphisms. So this is very general. You can assume any degree of regularity. So you can build all sorts of subgroups of homeo of I, or diff K of I, or of the circle if you want, which are built out of copies of Thompson's group F. So the motivating definition is of what we call a chain group. This was due to myself and Yash Loda. So if you have J1 to JK are a chain of intervals. So by a chain, I mean just something like this. And F1 to FK homeomorphisms, such that the support of Fi is exactly equal to J sub I. So I'm thinking these are open intervals, and then so Fi is the identity outside of Ji, and it has no fixed points in the interior of Ji. And then you assume that so F1 to Fk is a chain group if you assume that Fi plus 1 is isomorphic to Thompson's group F for all I.
So what's Thompson's group F again?
So Thompson's group F, this is the group
Generated by two homeomorphisms. No, this kidding.
group of piecewise linear homeomorphisms of the interval I with dyadic breakpoints and all slopes are powers of 2. Okay. So you get this class of groups. So, I mean, one can be a little bit sloppy. So the chain group can either be, you can view it as just an abstract, finitely generated subgroup of the group of homeomorphisms, but I like to decorate it with a choice of generators as well, although that doesn't really cause many problems anywhere. Okay, so So perhaps chain groups are really boring. I mean, who knows? I mean, if two chain groups are all just Thompson's group F, so maybe there's just one isomorphism type for each k. But one has the following result. So everything that I say about chain groups is joint with these two guys. So here's a theorem. So if G inside of homeo plus I is n-generated, then G embeds in an n plus 2 chain group. So you take any group of homeomorphisms at the interval whatsoever, abstractly as a group, you can embed it inside of a chain group which has n plus 2 generators here. So then you can, so this doesn't quite say that they don't necessarily fall in one isomorphism type for each k, because you can still have lots and lots of subgroups. However, there's this old result of I think it's Bernhard Neumann, which gives, there exist uncountably many two-generated groups. So he writes them down as some uncountable family of quotients of the free group on two generators. And the small observation that we made here was that they're left orderable. And in particular, there are uncountably many non-isomorphic, pairwise non-isomorphic subgroups generated by two elements instead of homeo of I. And so what this implies is that there exist uncountably many pairwise non-isomorphic chain groups. So if you were to apply this theorem directly, it should say when k is at least 4, but it turns out you can do a little bit more work and you get for k at least 3. So the moment that you allow 3 homeomorphisms, like in this situation, things go quite haywire. So,
Sorry, you're
yes.
saying that subgroups will change, right?
yeah. So sorry. No. They're. So every chain group is countable because it's finitely generated, and so if there are only countably many isomorphism types.
Right. No, I'm just asking about the definition of chain groups. Right.
Yeah. Wait, I'm sorry, confused.
Don't worry, I'll talk to you.
Okay. So it's supposed to be talking about regularity, so what about that? So it turns out that these uncountably many quotients that Neumann produces, they all contain copies of the integral Heisenberg group. Neumann's groups all contain this H sub z, which is xy. So this is a non-abelian nilpotent group, and there's this classical result of Platt-Thurston, which says if n is a finitely generated, or is a finitely generated nilpotent group, you don't need this assumption. If it's a nilpotent group inside of diff2 of n, where here this is again compact one manifold, then n is abelian. So this is again in sharp contrast here to this Frank's paper. So regularity again makes a huge difference for nilpotent groups. And so this corollary that we get is that so there exist uncountably many finitely generated subgroups of homeo I, which do not, I guess are not conjugate into diff2.
They're also not conjugate to each other?
Well, yeah, they're not isomorphic to each other, so yeah. Okay, so in the last 3 minutes, I'll mention so from what you may gather here, chain groups are very diverse, but they also have some very uniform algebraic structure, which reflects the behavior of Thompson's group F. So, first it's a proposition because it's fairly easy. So, let G be a chain group. So, assuming that it has at least 2 generators, not just Z. The center of G is trivial. And the second has an immediate analog for, is a generalization of what happens for Thompson's group. So, G, a chain group, then either you have the following. So the commutator subgroup of G is simple, which is what happens for Thompson's group F, or there exists a wandering interval J in the support of G, namely the union of the supports of the generators. And if you look at the stabilizer of the total orbit of J is a normal subgroup of G, and G mod stab Gj is naturally a chain group. If you call it H, and then the commutator subgroup of H is simple. So this isn't a vacuous dichotomy. This does happen sometimes when we pick up such examples, and by sort of this Denner blowing up an orbit argument. And I guess the last thing I'll say in 30 seconds or 10 seconds is that this theorem gives you uncountably many pairwise non-isomorphic simple subgroups of the homeomorphism of I. So I'll stop there.
So can you say a word about the proof of that first theorem you stated up on that upper right-hand board?
Yeah, sure. So about the right angled arc group, not active.
Yeah.
Yeah, so, this is originally, we found this because of, it was an error in another theorem that we tried to prove, which was discovered by Jonathan Bowden, who I think is in the audience here. But so it's basically just the enemy then was the mean value theorem, and we spent a few years trying to turn it into our friend. So if we use the backwards convention for right-angled arc groups, it turns out that P4 is isomorphic to its complement. So if I take A, B, C, and D, and now I declare two of these to not commute if they're adjacent, then I can reflect this arrangement of vertices by an arrangement of intervals like this.
Right.
So what one could show is that if you have any faithful action of A of P4 on any one manifold, you don't have to assume compact, then you have infinitely many configurations of intervals that look like this, namely the support of this homeomorphism A, and of B, and of C, and of D. Actually, you need twice differentiability for this. You have infinitely many intervals like this one, strewn all over the place, and B, and C, and D, but arranged in this sort of pattern of a chain like this.
So you're saying this would be contained inside a chain group, is what you're saying?
Well, that's true, but we didn't know what a chain group was when we proved this. So, and moreover, if you take this point, then if you apply B to X and C to it, then this lies in the support of D. So this sort of, not only this sort of configuration of intervals which reflects the graph theoretic structure has to occur on infinitely many places, then you also have to have this sort of fast movement of a point. Okay. And once you have that, then you say, well, because of compactness, this has to happen on infinitely many small scales. And so then you can argue using the mean value theorem that this condition forces B or C or one of their inverses to have a derivative that just blows up. So that's how you prove it.
Other questions? Okay, let's thank Thomas.